All right, hi chemistry students. This is a video on 11.1, chemical equilibrium. I thought a really good example of chemical equilibrium was actually what we worked on a couple weeks ago when we were talking about the depletion of the ozone layer as a result of the catalyzed reaction of ozone breaking up into oxygen when light, HV, hits into it. So we learned this reaction, we learned how it happens. We said that, hey, if you have ozone, if light hits it, then it's going to break up into something that looks like this. Now, of course, we know that oxygen can't be by itself, right? And so once this happens twice, right? So basically this happens 2 times, and then you get 2 of these guys. And then these guys are going to come together and they're going to form another oxygen. So we're actually going to have 3 oxygens all together, because 1, 2, 3. And so yeah, this is how we get this reaction. This is how this reaction kind of mechanism goes. And so we also could write it as 2O3 yields 3O2. Again, this is catalyzed as a result of Cl and Hv. Interesting little reaction. And so we know this reaction. We learned it. We're familiar with it. I just reviewed it with you. But what we didn't know, what I didn't say to you, is actually that this reaction can also be reversed. So not only can we go from ozone to oxygen, but we can also actually go back from oxygen to ozone. And so despite the fact that I didn't write this, actually, there should be 2 arrows. There should be another arrow that's going backwards. Basically, what we didn't say is that this reaction is reversible. And actually, we haven't talked about that at all this year. We haven't talked about the reversibility of reactions. What you're taught in 8th grade middle school physical science is that chemical reactions are reactions because they aren't reversible, because you can't make them go back, and that's kind of a lie. I mean, here's the thing, right? We're always trying to simplify things in order to help you guys understand them at a certain level. But sometimes what we say is a lie because, you know, that's all you can take at that moment. But no, it's actually not true. Reactions are reversible, and actually most reactions are in some level reversible. It's just the fact that some reactions are less reversible than others. But all reactions technically, at some level, are reversible. We can go back and forth. And so here we can, ozone will be indeed broken down into O2 as a result of light hitting it, but also we can get that reversed back into ozone. And this is a good news, this is a good thing, right? Because think about it, right? If we have ozone in our atmosphere, and this is protecting us from the sun, and if light hits it and it turns into oxygen, oh no, right? Like that's horrible, right? And so all of our ozone would be depleted really soon. But the thing is, it goes in a cycle. It goes to oxygen and then it goes back into O3. Now, as you're seeing, there is this back and forth. And so the question is like, okay, well, how much is there a back and forth going on, and where are we going to end up? And that's the question at the heart of equilibrium. Where are we going to end up? And that's what we're going to try to understand today in this video, in this lesson with equilibrium. When you think of equilibrium, I want you to think of a teeter-totter. On a teeter-totter, when you're a kid, right, you can go back and forth, right, depending on how much balance you have, right? And that's what we're ultimately doing with equilibrium. We're not going to necessarily have the same amount on both sides, but the point is there is some level of, we got products, we got reactants, and we're going to be able to there's going to be some amount on each side. And so, and we're going to be going back and forth. And so there's 3 situations that you can have with equilibrium, with a reaction in equilibrium. There's 3 types of kind of scenarios of sorts. I'll go through one by one. So let's say, for example, we have this reaction. A goes to B, and it can also be reversed. So A is in equilibrium, we say, with B. The first situation is it could be a reaction where the products and reactants are equally favored at equilibrium, right? So the question of where will we end up, right? As we're going back and forth, you could have a situation where A and B are totally equal at equilibrium. We can see that here in this graph where, as time on the y-axis increases, the concentration of A decreases, and the concentration of B decreases until we reach TEQ, time of equilibrium, where they're both equal to one another, right, where the lines have converged. We can notate this in a couple of ways. We can do this A goes to B and back to B and make this arrow, the back and forth, equal to one another. We also write the KEQ, the equilibrium constant, is equal to 1. More on that later. So that's the first situation. The second kind of situation scenario for an equilibrium reaction is you could have a reaction where products are favored at equilibrium. What that looks like is this, where we have A decreasing over time and B decreasing over time. And once we reach, we're probably TEQ around here. Once we reach TEQ, which is when the products and the reactants are equal to one another, or sorry, not when the products and reactants are equal to one another, when the rate of the products and the reactants, the rate forward, rate reverse, are equal to one another, we have much more B compared to A. And so we can notate that one like this. A goes to B, and B doesn't really, there's not much of a reversed reaction here. Mostly we're just forming B, and the backwards is kind of weak. And in this situation, we say KEQ is greater than 1. And then the last thing, sorry, actually, it's on this page. The last situation we can be in is where our reactants are favored at equilibrium. So the reaction occurs, we reach TEQ, but here A is more than B. We have more of our reactant at the end. We say here that there's not much of a forward reaction, there's a big reverse reaction. Here KEQ is less than 1. And so these are kind of the 3 situations you can be. And so that brings me to the definition of equilibrium. The definition of equilibrium is a reaction has reached equilibrium when the rate forward of a reaction is equal to the rate reverse of a reaction. And so it looks like nothing is happening. There's no observable change in our chemical reaction, but there is. We are going back and forth. It's just, it's equal to one another, and as a result, it seems like nothing is happening here. And so a reaction has reached equilibrium when as a result, there are no observable or net changes, though there are still technically, we still technically are going back and forth. It's just the fact that at equilibrium, they cancel out each other because RF is equal to RR. There is no net change. Now, of course, these things are better understood via some practice. And some example problems, and so let's take a look at a couple of those for you guys. Before we do that, though, actually, sorry, one last little theoretical thing is you need to know the definition of KEQ, right? And so KEQ is equal to our products, the concentration, sorry, or products over our reactants. And so, for example, here, if we have say we have AA plus BB is in equilibrium with DC plus DD. Here, KEQ is going to be equal to concentration of C to the power of C times concentration of D to the power of D over concentration of B to the power of B over concentration of A to the power of A, where, right, C, D, B, A, these lower cases are all the coefficients, and then, of course, these big ones, right, that's where we're getting these concentrations from. Okay, so that's KEQ, and so that's its definition. And so now let's apply this theoretical understanding, these theoretical ideas, to a couple of practice problems. So Number 1, determine the equilibrium constant KEQ for each of the following reactions. Say we have H2 plus I2, and that's in equilibrium with 2HI. What is the equilibrium constant for that? And then we have another one. We'll get into that in a second. So this one, right, we said KEQ is equal to, KEQ is going to be equal to the concentration of the products over the concentration of the reactants. And so here, well, our product is HI, right? And we remember we saw that this coefficient needs to not be the exponent, right? And so we're going to put that as the exponent, and then over H2. And you could put 1, but you don't really need it, times I2. And again, so we don't really need that one, right? And so I'm just going to box this. This is my answer. KEQ for this equation, for this equilibrium reaction, is this. That is its equation. That's it. Pretty easy, very doable. And so now let's do B for this reaction. What's KEQ? Well, again, products. So HbO2 4 times CO, and CO is to the power 4, over HbCO4 times O2, that's to the power 4, and that's KEQ. KEQ for this reaction is the following. There you go. And so that's how you determine KEQ, the equation. Now how can we get actual numbers here? So instead of just having HbO2 4 or CO, right, how would you get numbers? Well, they have to be given to you, and then you can solve for it. And so let's take again A, right? This time I'm gonna actually give you the concentrations. Can you find the specific numeric value of KEQ for this reaction? Well, you can, right? Because we know KEQ, right, we just wrote, is HI squared over H2 times I2. And so now all I have to do is plug in, right? So we put that there, and we put these guys here, right? And so for HI, it is 0.80 squared. H2 is 0.10. I2 is 0.05. And unfortunately, I do not think I have my calculator. Otherwise, I'd show you guys how to put it into your calculators, right? But it's literally just, think of the brackets as parentheses, okay? The brackets are basically just parentheses. Okay, so just put into your calculator 0.80 parentheses squared divided by 0.10 times 0.05, and you will get, once you put that into your calculator, you should get, and this is how you know you put it in right, 128. So that's how we get a specific numeric value of KEQ for this reaction. Bonus question. For this reaction, what type of scenario are we in? Are products or reactants favored? Right, and if you think about it, right, you will remember that we are actually in scenario number 2 here, right, where KEQ is greater than 1. KEQ is 128. Yeah, that's greater than 1. And here, indeed, yeah, we're making a lot more HI. The molarity, the concentration of HI, is much greater than H2 and I2. And so we're kind of in this situation where we're making a lot more product at equilibrium. Again, at this stage, nothing is happening. It seems like, you know, there's no movement. It looks like nothing's happening, but there is a back and forth. It's just the fact, though, that products are ultimately favored here because there was more of a drive towards that. But ultimately here now at this point, RR and RF are equal to each other. There's no changes, but we end up with products being favored. So products favored. So just a little bonus question there. And so that's equilibrium. Hopefully that helps you guys with your a little bit of a theoretical understanding. I will say there's other YouTube videos that also have much better graphics and motions and everything than this. This was just, I gave you the basics, showed you a couple of graphs, and showed you how to do 2 of the most important practice problems. But by all means, if you want some more visuals, take a look at some YouTube videos. I've seen really good ones which have very nice infographics and pictures, drawings. That maybe will help you out more. So take a look at those. Let me know if you have any questions. You guys are doing great. We're almost to the end of the year.